Green's theorem. What is a Green's theorem? Green's theorem is one of the most important theorems in vector calculus. Green's theorem is mainly used for the integration of line combined with a curved plane. This theorem shows the relationship between a line integral and a surface integral. Green's theorem is used to integrate the derivatives in a particular plane. If a line integral is given, it is converted into surface integral or the double integral or vice versa using this theorem. Let's proceed to the examples of Green's theorem. Example number 1. Use Green's theorem to evaluate the given line integral square root of 1 plus x cubed dx plus 2xy dy, where C is the triangle with the vertices 0, 0, 1, 0, and 1, 3, oriented clockwise. And this is the figure that we drawn. The curve C can thought of the union of the three line segments, which can be parameterized easily, but doing the line integral directly would be hard or impossible. But Green's theorem converts the line integral to a double integral over the region D, enclosed by the triangle, which is easier. Let P is equal to square root of 1 plus x cubed and Q is equal to 2xy. We can now calculate that partial Q with respect to x is equal to 2y and partial P with respect to y is equal to 0. Then, using Green's theorem, our line integral becomes integration of p dx plus q dy is equal to double integration of partial q respect to x minus partial p respect to y dA is equal to double integration of 2y dA. We now need to figure out how to parameterize the region D so that we can set up the limits in the double integral. It's a nice right-angled triangle, so it can't be that hard. Think of transversing the whole region D. Let x vary from 0 to 1. For each x, we let y vary from 0 wherever it hits the slanting side of the triangle. Now that side is given by the equation y is equal to 3x. As you can calculate, since it passes through 0, 0, and 1, 3. So the maximum y height you need to go when you are at x is 3x. So with the limits, the line integral becomes double integration with the limits of 0 to 1 and 0 to 3x, 2y dy dx. Notice that dx is on the outside since we are varying x first, and for each x we then vary y. We can evaluate this integral easily. Double integration with limits of 0 to 1 and 0 to 3x, 2y dy dx, and applying the first integration, it will be equals to integration of 0 to 1 y squared limits of 0 to 3x dx will be equal to integration of 0 to 1 9x squared minus 0 dx. Then applying the second integration will be equals to 3x cubed limits 0 to 1 is equal to 3. So the final answer for this given line integral of square root of 1 plus x cubed dx plus 2xy dy is equal to 3. Example number 2. Use Green's theorem to find the line integral of x squared y dx minus x y squared dy, where c is the circle equals to x squared plus y squared is equal to 4, going counterclockwise. To use Green's theorem, let's figure out what our p and q are and compute its partial derivatives. So p is equal to x squared y and q is equal to negative xy squared. We can calculate that partial q respect to x is equal to negative y squared and partial p respect to y is equal to x squared. Then, using Green's theorem, our line integral becomes integration of p dx plus q dy is equal to double integration partial q respect to x minus partial p respect to y dA is equal to double integration of negative y squared minus x squared dA is equal to double integration x squared plus y squared dA. Now d being a disk and the integrand being the way it is, the integral is begging to be done in polar coordinates. So negative double integration x squared plus y squared dA is equal to negative double integration the limits of 0 to 2 pi and 0 to 2 r squared multiplied by r dr d theta. Notice that the upper limit for the inner integral is 2 because r varies till 2. D is the disk of radius 2. Also, don't forget that the area element dA in polar coordinates is r dr d theta. So let's finish the calculations. Negative double integration with the limits of 0 to 2 pi and 0 to 2 r squared multiplied by r dr d theta. So applying the integration, it will be equals to negative integration 0 to 2 pi r raised to the 4th over 4 limits 0 to 2 d theta is equal to negative integration 0 to 2 pi 4 d theta is equal to negative 8 pi. So the final answer for the given line integral of x squared y dx minus x y squared dy will be equal to negative 8 pi.